Okay, I've switched to the whiteboard. This should not give us an issue. Okay, great. All right, so as you know, this part is more like like the algebra, the algorithm itself. So I will go over the details and then we'll do some exercises and I may give you some problems, okay? So that you would solve by hand probably. And we'll do some, exercises. All right, so RSA, you already know kind of some of the intuition. And now we're going to get into the details. Okay, the RSA just comes from the names. So RSA is a cryptographic algorithm which was developed by Ron Rivas, Adi Shamir, and Leonard Edelman at MIT. So it was developed there, and it's named after them. So they, as I said, created this as a solution to the call that was made for this type of a framework. I think Diffie-Hellman, or there's other techniques like Al-Gamal, I think, et cetera, that were proposed, and they're kind of secure, but this one is the best, it seems. All right, so the algorithm was developed around 1977, and it uses both public and private key. All right, so we're gonna go over the ideas of this, the algorithm, and there's quite a bit. So instead of giving you a ton, what I'm trying to say is instead of giving you like too much detail, right? Initially, I'm just gonna give you some of the more important ideas, right? Like 5 to 7 ideas, and then understand that, and then we're gonna drill down into each individual idea in more depth, okay? But it's not really that complex. So let's talk about the algorithm itself. So this is the algorithm. Okay, so it's a fun thing. It basically uses prime numbers. So you should, step number 1 basically is you need to pick or select 2 random numbers, okay, which are usually described as P and Q, and they should be different. So they should not be the same. All right, so randomly and independently select, and this is key, 2 large prime numbers. If you select 2 small prime numbers, you'll break RSA, as I will show you shortly. All right, so let's say select, let me switch. So select 2 large, and we talked about how 496-bit, right? 496-bit. One of the problems that we will do in the lab is actually increasing the size of the key. And as you will see, the more you increase it, the slower it's going to be. It's going to become very slow. So select 2 large prime numbers. Prime numbers, P and Q. And we want to say that P and Q should be different. Okay, they should not be the same. So it's like 3 and 5, 3 and 7 would be very large, very small prime numbers. Then you're going to calculate n. So you already have seen n, right? And n was what? P times Q. Okay, that's the n that's going to make up both the public key and the private key. So it makes part of it. So calculate n, which is the product of P and Q. Then step number 3, I'm going to go to another page. Okay, so step 3, now you're going to calculate a value which is called phi. So usually denoted by this letter. Sometimes just when I write the code, I'll just do phi like that. Okay, but basically the same variable. And this one is calculate a phi, which should be P minus 1 times Q minus 1. Okay, that's, so far it's like super easy, right? Except that they should be based on really large prime numbers is all. Step 4, And this is where it starts to become a little bit more complex. So I'm just going to, for now, say with additional conditions, etc., and then we're going to drill down into what that means. Basically, you're going to select an integer E. Okay, this is called the encryption exponent. Sometimes it makes up one of the two elements of the public key. So you're going to select E such that you're going to have one E5. Okay, so basically that means that it should be between 1 and 5, which 5 is, we calculated already up here, right? And also, and meets other conditions as well, which we will define later, okay? So select an integer E such that this and meets additional conditions. We'll do some exercises to kind of explain this, but let's just say this for now. And meets, select an integer such that and meets additional conditions. Additional conditions, okay? So, e.g. GCD. All right, so just as reference, we will come back to that function in a sec. And 5, so I'll do that in the next part. That's actually the last part of this. Step 5, we calculate D. We want to calculate D. And this is the decryption exponent, which makes up one of the two parts in the private key or the decryption key, okay? So that's kind of the idea. So this one, calculate D such that, and then we're going to have a formula here, which is going to be D times E mod phi equal 1. Okay, that's it. So see how I was saying that this is a lot like algebra, okay? Mod is an operation. I will show you how to calculate that in Python, right? We'll do an exercise just of mod, and I'll give you what it means, but you probably used this before, modulus operation and remainders, right? So we'll take a look at that. So why does this work? Well, it works because if you look back, we already have phi, right? We defined it back here. This is 1, the number 1. And this E we should have already from the previous step here. So given all these terms, we are able to find for or solve for D, okay? So that's basically the algorithm. So D times E mod phi equal 1. Now, what is this process for? Is this process for all of RSA? Actually, these 5 steps are for calculating the key, the public and private key, okay? So these are the 5 steps for calculating the public and the private key. So then that gives you, as a result, a public key and a private key, which is what you will be using. Now, obviously, when we use OpenSSL or PyCryptoDome, those are really nice because they just give you a file and it's kind of a mysterious file. But if you look really deeply into it, you will see that these are the parameters that are inside that file. Okay, so the public key, as you saw in the slides, is n comma e or e comma n, it doesn't matter. And then the private key was what? Who remembers? dn, right? Yeah, exactly. So dn or ne. And remember, it in the slide, it even said where n is the same for both. So you see, now this is what you make available to the entire world, right? But you make both E and N available to the entire world. So really, a hacker, etc., would already have one element of the private key, right? N, but they just don't have this. This has to be kept a secret. You will also find that N is the same, and it's a very large number. But you will also find that E is actually much smaller than D. D is going to be really long, and this is one of the things that we will, especially with OpenSSL, we'll play with to get a feel for how long they are. And that's basically how you generate the public and the private key. That's the math behind it, basically. Now, let's say that you want to actually encrypt. So then you have those elements, and now we need the procedures for encrypting and decrypting. So we're going to assume in this case that we have a message, and we're going to call it M. So this is going to be the plain text. So that's the plain text, okay? And then we're going to assume that C is the cipher, all right? So it's the thing that we want to, achieve confidentiality. Generally, this would be the AES or DES secret key. So again, once again, we use algebra to calculate C. It's going to be M to the E. So it's raised to the power of E mod N. And that's it, actually. So to encrypt, we just follow that. Okay. We'll do an, if we have several numbers, I'll do an example later. We'll take a sequence of numbers, like say a key, and we're going to encrypt them. And you'll see one interesting thing about this approach is it's like, how in block ciphers where we're able to pad and things like that, or the algorithm sometimes started at 32, but then we made it 48, and then it came back to 32. With RSA, let's say that we have a number, 128, right? So the number has 3 digits. After we do the encryption, it has 4 digits. So it might be another number like 4,655, and it makes it bigger. So it's a way of not knowing the original size. So anyway, so this is the cipher, how to get C, the encryption. Okay, maybe I should say, so this is to encrypt. Okay, that's how you encrypt. And then to decrypt, as you might imagine, is similar. So now we want to decrypt, and that's going to be C to the D mod N. And that's it. That is the techniques that we use to decrypt. So one of our first examples on Thursday will be to implement basically these functions in a very simplistic way. So we'll implement all of this in Python. Any questions? This is RSA basically. Now there are some, as I said, some additional things that we have to drill down on, and we will. But let's do an example, okay? So I have several examples of how to do this calculation. This first one is very straightforward, and it's just meant to show you how these things can be computed, okay? Now there's a flaw in this problem, and I may do this on the exam, right? Or in one of the quizzes that we do, I may give you an example and tell you there's a flaw. So you need to understand what the flaw is and tell me, okay? So let's see if you guys can tell me. I'm not going to say anything, but at the end, tell me what the flaw is, okay? So let's go ahead and do this one. So this is, let's say RSA toy example or very simple example, okay? Let's just say RSA example. Okay, so remember there's a flaw in this. All right, so choose, what's this first? So we're gonna first select the keys. We're gonna have a message that we wanna encrypt. The message is 7. So our plain text message is the number 7, and that's what we want to encrypt, okay? All right, so we need to get pub and private, right? And that means for the pub is going to be E comma N, and for the private is going to be D comma N. So we need to get those parameters and then use the equations to obtain our result. So the first step to get the keys is, say, 1, choose 2 random prime numbers, P and Q. So right now, obviously, I'm not going to do the very large numbers because it would be too difficult. We'll save that for like the big num lab, but I'm just going to do tiny numbers, so tiny it's insecure completely. So let's do P equal 5 and Q equal 3. Again, this is just to illustrate what we're doing. So step number 2 then is to calculate N. So that should be P times Q, right? So that would be 5 times 3 equal 15. And we already have our N. You see that? So then over here, E, D, and then this is 15. This is 15. Does that make sense? Okay. Number 3. Now we need to pick phi, right? Calculate phi for phi. And we establish that that's P minus 1 times Q minus 1. Okay, so that should be what? 5 minus 1, and then 3 minus 1. So that's going to be 4 times 2, right? And that's 8. Okay, so that's basically phi, the other variable that we need. Okay. All right, now the next step is that we would need to pick a value for, so the next condition is we need E phi, right? So phi is 8, 1 E, and it needs to meet other conditions, something called the GCD. So we'll do an exercise a little later that's more in depth, okay? But in this one, let's just keep it simpler. So I'm just going to say we would need a value here, right? So in this case, E will be, let's say 3, okay? And then I'll show you guys how we would actually, because it's involved how we need to try several numbers, check the GCD condition of them between these, etc. And we have to compare it for every prime number, etc. So there's quite a bit of steps. All right, so we'll come back to that. But let's say that E3 equal 3 meets this condition, obviously, and would also meet the GCD condition. So now we have E, okay? And then the next step is we have E. So what was it? 4? Yeah. So this would be 5. Now we have to choose D, okay? So the equation for this one we defined previously. Let me just find it. So we said that D times E modulus phi equal 1. Now we should have all of these parameters already, so we should be able to just solve for D. Okay, so I'm going to do here D, E is 3 mod phi is, it's like 8, I think. 8, yeah. All right, and then equal to 1. Okay, and so we would need a number here that solves this equation, right? Not every value will solve this equality. In the end, all of this needs to become 1 and 1, and it's equal to 1. Do you see that? It's like a check that happens. And so we implement this in the algorithm itself, right, and find this value. So in this case, for now, let's assume that D equal 3 solves that, right? So we have now the parameters that we need. So now we have all the parameters, and now let's proceed to do the encryption and decryption. Okay, as I said, this is a very toy example. We'll get to the details of this later. So we have the public and private key. Now we want to encrypt our message M7. So we saw that the equations for this were here, right? So this is what we're going to use, the mod operation. So I'm going to do cipher. This is the encryption part first, right? Encryption. So cipher equal M to the E, which in Python, this will be a caret mod N. Okay, so this should be 7. What's E? You guys remember? What is it? 3? Mod, what was N? 15, I think it was, right? Was it 15? Yeah, it's 15. Do you see that? And then this would give us our cipher. We will implement this in Python on Thursday. And I believe the value for this is 343. So when you do the example on Thursday, you should get 343 in the number. And that's the encryption. Does that make sense? All right. Now, the decryption part would be, as you saw in the equation, wait. The cipher should actually not be 343. I read that wrong. Sorry about that. So it's 7 to the 3. Yeah, so actually 7 to the 3 is 343. Sorry about that. All right, so the answer should be 13, actually. So this is the value that we should get. All right, so C is 13, and that basically 7 becomes 13. So the plain text is 7, the cipher is 13, okay? As I said, we will corroborate this on Thursday in the code. Now, to decrypt, we do M, right? And that's going to be C to the D mod N. Okay? So we plug in the values here. This is 13, correct? What was D? Three, right? So we found it to be 3. So it's 3 mod 15. And the decryption, of course, should be the original 7. Does that make sense, guys? So this is just a simple example. It's going to be the most basic example that we do. Don't worry, it's going to get much more challenging than this. So now I ask you the following question. I said that there is a flaw in this. Let's see if you guys can spot it. It's complete at this point. What do you think is wrong with it? Yes. They're the same, right? Very good. Very good observation. If you notice, they're the same. So I didn't intentionally, right? I didn't write it out, if you notice, but they are the same, right? And so that's not correct, right? So if we know that so we know N is 15, and we know E is 3, and D is 3, right? So that would effectively make, so that would make the public key what? 3, 15, but that would also make the private key 3, 15. If you're making the public key available, which you are, then you would know that the private key, and so that doesn't work. Does that make sense? So this is the flaw in this code, okay? Obviously, that should not be like that. Got it? All right, let's do one more exercise of these, and then you can implement this one too on Thursday, okay? This one I will do in, this one has better numbers, obviously. And a lot of this requires to write code, etc., unless you have like a nice calculator that does these operations, or maybe your iPhone does it. I'm not sure, so it might. So anyway, let's do another problem, okay? So this would be example 2, okay, of pretty much the same thing. We're gonna do like literally the same thing, just with bigger numbers, and I have like 5 of these problems, so they just get more and more detailed. All right, so let's call this one example 2. Okay. So again, we're going to repeat the exact same steps, just like we did before. So we want to encrypt the message. The plain text message this time will be 65. Okay. So we want to encrypt and decrypt. So we need first to get the keys, right? So we need, once again, pub and private. At some point, we will do an exercise with OpenSSL, which you guys know is like a very solid crypto. And there's ways that we can go into certificates or public keys and look at N and look at E. And you will see that they're very large numbers. All right, but here they're very tiny. So we need the public to be E, N, and we need the private to be D, N, okay? So let's start, follow the process again. Step 1, find P and Q. They should be prime numbers. So this should, it's an example, 61 and 53, okay? Just with these little numbers, it starts to get much bigger. Okay, so the numbers start to get bigger and bigger, so the operations get harder to do. I mean, you'll see one, the decryption is like a ridiculous number. Okay, so we'll see that in a second. All right, so and this is totally insecure. I mean, it's literally like 61 and 53. All right, so let's do step number 2. We want to get N and phi, right? So let's do N. P times Q. So that's going to be what? 61 times 53. And that should be 3,233. Okay? Okay, guys? Then we're going to calculate phi. So I'm going to do step 3 here. And that will be, if you remember, phi was P minus 1 times Q minus 1, okay? So this is going to be 60, because it's 61 minus 1, and Q minus 1 should be 53 minus 1, which is 52. So that is 3120, okay? Think about these numbers already, right? So now let's take a look. Let me give you step number 4. So on the exam, sometimes I may give you a question such as this. Okay, this is a type of question that I may give you. So you kind of have, I may say, okay, you need to select E, and I'll give you like a multiple choice problem. So you need to tell me which E you would select. So you have several options. So select E. And I may give you, the options will be like 7, 4,000, 3.5, and minus 6, something like that. So you have to select one of these as your E value, right? And so you'd want to think about how you would select this, right? So based on the RSA algorithm and your knowledge so far, which one of these two, oh, sorry, let's say 17 actually, sorry, 17. So which one of these would you select? Let's say A, B, and C. So which one of these would you select as E? And why? $17, right? It's pretty easy, right? But actually, this is important. It's not negative. It's not a decimal, right? It's not 4,000 because this is greater than phi, right? So I think, yeah, because 3120. So the condition was 1E 3120, and there's actually more to this because we have to, it also has to be what is called coprime, and it has to meet the GCD condition, which we haven't looked at just yet. There's quite a bit that goes, but it's basic. Why does it have to meet all those conditions? So the math works. The math will only work with certain specific numbers, but if you pick those very correct ones, it's unbreakable, right? And so as far as we know, so that's the key thing. So then you select, your answer should be A, oops, sorry. So your answer should be A or 17. So we can say that E is 17. Make sense? All right, so we've got that parameter. And then D, you already know, it's an equation given. Sometimes you see in the form of something called congruency, but don't get confused by that. You can just use this equation, which is pretty, I mean, it's very simple algebra that you can do by hand. This is the modulus operation phi. We'll talk about modulus. We'll do an exercise. So that one is as we proceed. And like I said, in Python, modulus is just done with a percentage. Okay, that's the operator. So, and then we said this should be equal to 1. Okay. So in this case, the value should be, and I may give you this because in the exam you won't have code. So D becomes 2753. Right, wherever it's like impractical to do a calculation by hand or a calculator, you know, because you would need script, I will give you this value. Okay, so in this case, 273 times 17 mod, what was phi? 3120 should be equal to 1. So when you do your exercises on Thursday, in the lab assignment, you can corroborate this one, should give you 1. Okay. In Python. All right, so now now you have the keys, right? So now let's go ahead and write them out. So we should have pub and private. Okay. So we said that this is E comma N, and this is D comma N. So that should be equal to, so who can help me? So I know D, because I can see it here, is 2753. What was N? N was not 17. 3,233. Yeah, 3233. You're thinking of the previous problem. So N is, yeah, thank you. 3233. Right? Then it would be 3233 for this one as well. And what was E? 17. You already see something that I was talking about that's very peculiar about public and private key. What else? What do you notice here? See if you're keen on things. What do you notice? What's the difference between the public and the private key that's kind of standing out? The E exponent is much smaller than the D exponent. Do you see that? 17 versus 2753. When we start looking at actual numbers, you will see how the size of it is very different. Okay. Does that make sense, guys? This is an important observation to make. All right, so now we have our parameters, so we can proceed to do the encryption. The original message was 65, right? So we want to proceed to encrypt and decrypt. Anyway, this is how we get the public and the private key. Are there any questions at this time? All right, so now let's proceed to do the encryption. So this is encrypt. So now let's take a look. So encryption should be C is equal to M to the E mod, and then mod N, right? Mod N. So then that's going to be C 65 to the, what's E? 17. Okay, mod 3233. Got it? And this should give you 2790. 2790. That's the cipher of 17. Any questions? Nope. All right, great. So now we want to decrypt. Okay. So how do we do that? We're going to say M equal C to the D mod N. So that's going to be M equal C is 2790. What is D?
2753.
2753. Mod. And what is mod? 3233. And that should give you 65, which was the original value. Have you ever done 2,790 to the 2,753? Kind of big, right? And this is not realistic P and Q. Not even close. So you see, right? That's, you know, this should like be very interesting to you. You know, that's a very large number. I mean, I encourage you to go to your calculator or your phone, compute this value, see if you can get it. Do it on Python on Thursday. Take a look at it, get a feel for what that represents. And like I said, keep in mind, you want N or P and Q to be a number of 4,096 bits or something, right? So it's really large. Any questions, guys? So this is kind of how I introduce this topic usually, right? So that's the general ideas. And that's kind of the general ideas, actually. And then from there, we just keep drilling down, test, you know, trying out the different algorithms and so on. There's a few, so we have about 9 minutes. So I'll give you a couple of definitions. Just hold them in your notes. GCD, what that is, so you kind of have a feel for it, and then we'll do an example just of how that's computed. There's a couple of algorithms, something called the extended Euclidean search that RSA uses, and and another one. Generally, those are just algorithms like the Viterbi algorithm, just famous people that wrote very interesting algorithms, and they're used for this approach. I will also give you a math example by hand of what mod is. Okay, so let's just wrap up today with these two concepts. Okay, so let's go ahead. So GCD is just a definition. You probably learned this in algebra, and you probably already know what it is, right? So what is GCD? Yes, greatest common divisor, right? And so GCD is that. So GCD, switch to red. So it's the greatest. And this is just basically a function that we have to check the E values that meet this condition between two numbers, right? So greatest common divisor. Sometimes maybe you learned it as greatest common factor or highest common factor. That might have been how you saw it. So the greatest common divisor, let's give a definition for this one. It's basically the largest positive integer that divides each of two values or two numbers, okay? So that's going to be the function. So let's just say, is the largest positive integer that divides each of two integers. Okay. All right, so that's basically the definition of that one. And then we'll do some examples later for that problem. Now, modulus, again, this is just outside of the context of RSA, just kind of the operation and what it means, okay? But basically relates to remainders of a division operation. So let's take a look at that one. So I'll just call it mod. As I said in Python, it is basically this symbol, which we will implement on Thursday. All right, so imagine we have the following. So this is from the previous example, D times E mod phi equal 1, right? So that was the relationship that we had, the equation. So that effectively became 2753 times 17 mod 3120 equal 1. All right, so basically we do the multiplication. 2,753 times 17 should be equal to 46,000. Should be equal to 46,801. Okay, and then mod 3120 and then equal 1. So this thing here is it's basically dividing. So let me try to do it in a different color. So what you do is really you do 46,801 divided by 3120. You see that? And so basically what you're looking for is whatever the remainder of this is, that's what you're looking at in this operation. So this should be 1, right, which is times 3120. So then that gives you 1560, right? And then you move down to 1, and then this is going to be 5. So then 5 times 3120 should give you 15600, and then the difference is 1. Do you guys see that? And that 1 is basically 1. That's it. So this is what we're doing. I'm not going to make you guys do this by hand, obviously, except, you know, for some exercises, but basically in code, this will need some kind of function that does this. Okay, so that's kind of the idea. Does that make sense? So that's the modulus operation and what we're looking at basically there. Okay. All right, so it's like 5:36. So yeah, I have to give you like little pieces like this, and then we will continue going deeper into this. As I said, this takes, you know, several lectures, but on Thursday, be prepared for writing some code, right? The toy example, just trying out a few things, then implementing one of the problems we did today, and then we'll start getting into the more advanced RSA algorithm. All right, so I'll try to have your exams graded this week. I'm working on that, and then we'll stop here for today.